What's up everyone? Happy 2023. My name's Dane. In this video, we're going to be having a look at a question that I got on LinkedIn, which is how come when I analyze failure data, it looks random and I can't really discern anything from it. So we're going to be having a look at causal modeling and how that helps us break down the data that we have and dig into what's really happening underneath. Let's get into it. So for this discussion, there's three things that we're going to be using. The first one is a free online tool for fitting data to Weibull distributions. If you Google Weibull fitting online, for me, it's the first link here, and it takes you to this free tool where you can plug in your life data and it will fit a distribution to it down the bottom. We'll come back to that in a second. The second thing that we're going to be using is an Excel spreadsheet here, and it has life data in it. We're going to be talking about the particular asset that we're analyzing. And we're going to be breaking down this set of data to try and derive insights from it. There's about 3,000 samples in this. Also, we've got a tab here for plotting some of the probability distributions that we get out of it, and having a look at that and sort of breaking down the subsets and how that changes the distribution around. Lastly, we have a blank presentation. We're going to be using this as like a whiteboard to map out our causal model. All right, back to our data. So this data, I'm going to create a link in the description below. You can pull it down and have a look if you wanted to. We've got 3,000 odd samples of life data for tires. And in the K column here, this number is in hours, and the tire failure samples are just numbered 1 to 3,000. The first thing that people typically do is they say, well, here's all of my information. I'm going to copy this, jump over to the free tool or whichever tool you're using, paste the data in here. Let's give it a bit more room to move with regards to the shape parameter. And when we click compute, it'll fit a function to it here. And you can see from this QQ plot here that the average life is around 15,000 hours, and the shape parameter that we get out is 1.32. It's pretty close to random of 1. It shows some sort of relationship to age in that it's slightly increasing, but it's pretty much random over time. And this is the crux of the problem. People think, well, tires, they fail randomly, and I can't really do much to prevent those failures because they're random. And presumably the first thing that jumps to their mind is it's probably just punctures and, random impact objects on the road, that kind of thing. And so that's where they'll leave it. But there's something else going on here. If we look at the chart, it's not unimodal. There's 3 distinct sections. One down the bottom here, around the early life, where there's this kind of like vertical line. Then there's a section in the middle which is curved, and another cluster of high volume failures around the 50,000 hour mark. And so where do we start? Where do we begin to dig into this data that we have? And one of the tools that we can use is called a causal model or a causal map or a causal diagram, to kind of map out how we think a tire would fail. And then that informs us as to how we should segment the data and look at various subsets of this overall population. All right, we're going to jump over to the whiteboard and start to map out what we think leads to a tire failure. The process for mapping this out is very similar to, let's say, root cause analysis investigation. Essentially, it's a cause and effect chart or causal model. We start with the end goal or the end event, which is tire failure, which is what we have the data on. And we start to think about what can lead to a tire failure. So we're going to make a few assumptions here, and we can figure these out as we go and as we draw the connections between the various elements. The first thing I'm going to say is that I think tire failures can happen in one of three ways. The first one is punctures. Okay. The second one is, let's say, wear or use. So this is where the tread has been worn down. And lastly, let's say stiffness. And the mechanism that I want to model here is when a tire becomes, old, the petroleum in the tire causes the tire to harden, in which case it doesn't offer the same grip as what it's designed to do. So most tires have a shelf life written on the side of the tire, and I want to use this as one of the ways in which it can fail. Now, it's important to understand how those failures were classified in the first place. You really want to go back to the people that collected the data and who took it and kind of decided what constitutes a failure. Is it failure of function? Is it complete demolition of the tire? But for this case, we're going to assume that whenever that tire gets called up by the maintainers as being not fit for purpose anymore and thrown out, that constitutes a failure, even if it is end of life and stiffness. They have to account for all of them. And so that is included in the data set. All right, so I'm going to insert a couple of shapes here to show the causal direction, which is that a puncture causes a tire failure. When the tread is worn, it also causes a tire failure. And when it becomes too old or too stiff or too brittle or whatever you want to call it, it's marked down as a tire failure as well. So this is the starting point. And what you'll notice is that these are sort of like the modes of failure for a tire. So it can be punctured, it can be worn, it can be stiff or brittle. And we're going to, in a second, have a look at what causes these failure modes to happen and extend the chart out here over to the left. But this is a good place to start. So the first thing that we'd be looking for in the data set is there any way to identify how these modes of failures were categorized? And we can start to look at the subset of data that relates to punctures, the subset that relates to worn tires, and the subset that relates to stiff tires and thrown out. So I've put the total population results from the Vable fitting tool into this results charts tab of the data spreadsheet. And now we're going to have a look at the data again, given that the operators and the maintainers have given us additional info on how those particular tires have failed. And that's shown here in column J, and we've classified that as the mode. The first mode that we're going to have a look at is the puncture failure mode. And I'm going to copy that data, jump across to the free tool again, paste it in, compute the results. And what we're dealing with here is, looks a bit better, looks like a unimodal line here. There's something else going on at the top, which we can dig into in a second. But again, it's pretty random. 1.24 and 19,733 on the scale parameter. I'll plug that into the results charts here as well. What was it? It was 19,733 and 1.24 shape. And this was a subset of punctures only. All right. Let's do that again for the next failure mode. And we'll look at the wear one second. Copy that information. Again, paste it into the free tool here. Compute the results. Uh, 1.53, 13,693. And these were wear only. And lastly, let's look at the stiffness ones. Jumping across to the tool again. And the chart here, oh, this one's interesting. So this one, it has a very, very high shape parameter, which indicates high predictability. 53410, 53410, and the shape parameter was 37.37. And this was okay. So what this is telling me is that 53410 works out to be around about 6 years, and let's assume that that's the life of the tires. I'm not sure exactly what the life of the tires are. They could be 3 years, 5 years, 6 years. I really don't know. But there is a very, very strong relationship with around about the 6-year mark that all of the failures get categorized as being too stiff. So from those results, we're able to predict when the stiffness mode will occur with pretty high degree of certainty, but the wear and the punctures are very close to 1 in terms of its Weibull distribution beta parameter, which means there's a high spread, which means it's pretty close to random. But we can do better if we have more information and more data. And the question is, what information and data can we get a hold of? What do we have? And what do we need to inform this type of model? So we need to go deeper into this causal diagram. We do that by looking at what causes each of these failure modes. So let's start with the bottom one, stiffness. Now, we already have a pretty good prediction for this. And so I think that the only cause of stiffness is time or age since production. And so we'll leave that there to start with. But for the others, what causes wear? Well, there's probably a few different things that cause wear. Let's call the abrasiveness of road as one of those causes. Let's say utilization. So the more that you drive, the more time you spend on the road, the faster it wears. And let's say the other one is speed, how fast you're going. Okay, so we come at this from kind of like a engineering first principles point of view. What do we think are the influencing factors on wear? And we'll connect those up. So speed is the cause of wear. If you don't go very fast, you probably won't get much wear. If you don't use the car at all or use the vehicle at all, then you won't get much wear. And similarly, if you drive on glass or something like that. And what I want to call out here is the different abrasiveness of, let's say, road versus mud versus dirt. Okay. The other thing, punctures, is probably also a function of the same 3 variables. Okay, speed, the faster you go, the more ground you cover, the more likely you are to hit something, let's say. And maybe it's not a function of the abrasiveness of road, but let's say road surface. Okay. Or you could even call it potential for, foreign objects being on that road. All in all, I think the last thing that you could bring out is something like road type. Okay, and let's say that the road surface is a function of road type, but also it is a influencing factor on how fast you can go on that particular road. All right, so this is the sort of set of causes that can lead, or the influencing factors that can lead to punctures and wear and stiffness. And this gives us a good idea of where we should be looking for other types of data that we can use. Now, we're kind of completely at the mercy of what data is available, but it may inform some of your data collection and data capture programs as to where to look. This brings us to a really important concept, which is that if we understood everything that causes every subsequent event, which causes every subsequent event, it's kind of like that the world is deterministic point of view. And we should be able to predict down to the second when a tire would fail. But the problem is that we can't because we don't know everything. And so what happens is the boundaries of this causal model that we're building is what determines the variance in the output. When there's data that we can't get, when there's things that we don't know, when there's relationships that we don't understand, that's what brings the variance or randomness into the results. And you know, some things are just impractical to go and collect, and we have to live with that. So there's a limit to what we can actually do. But it's interesting to look at it from the view of the more things we know, the better we're able to predict the outcomes if we can understand the relationships between all of the different elements in this causal diagram. All right, rant over. Let's get back into it. So where do we start now? The first thing I'd be doing is asking for, do you have utilization or speed proxy data? And do we have any way to infer the road type or road surface that these vehicles were used on? And if we can get that information, we can start to look at subsets of wear by speed, by road surface, and by utilization. And similarly, subsets of punctures by different road surfaces, different speeds, and different utilizations, and see if there's anything there to uncover. So imagine that we do get that information, and the operators have said, oh, well, these tires were used on vehicles that operate in the pit, which is very muddy. Some are just transport vehicles, which operate on dirt roads, and some are our sort of long haul trucks and so on, which are just run on sealed roads. And we infer from those different road types an average speed. We can use a bit of sort of poetic license to generate our own subcategories just to see if we can uncover things. But the utilization data, let's say we pulled that from the car's GPS systems and so on. So they've given us that set of information now. And what I want to do is just look at the subsets of, let's say, wear. And the first thing that we're going to do is look at road types. So look at dirt, grab that life information. Again, jump over to the tool here, paste it in, and click generate. And what we get out of this is 1.6614.596. Repeating that for road wear and mud wear, we get similarly unpredictable distributions here. There is a bit of a difference between the characteristic life, and we see that the best performing terrain or road type is mud, presumably because of its lower speed. But it ranges anywhere between 10,000 hours and 18,000 hours, depending on the road type, but pretty random spread. It's telling us that we're kind of on the wrong track and we should be digging down other paths or other rabbit holes. The other option we've got to explore here is utilization. So let's see what utilization brings us. Now, one tip to segmenting the data is that for the particular branch of the causal model that we're looking at, in here we're looking at wear, and in particular we want to vary on utilization. We want to keep the remaining variables constant and open to all possibilities. Okay, so we want to filter by wear, but we want no filters on road surface and speed, and then we're going to segment by utilization. So jumping back to the spreadsheet here, we're going to make sure our filters on wear. We want the road types to be open, all of them selected, and then we're going to segment on utilization. So there's a bunch of various different utilizations here, ranging from 0 to 30%. The first thing we're going to have a look at is, let's say, the bottom quarter of those to see if it's any different from the top quarter. Again, we'll select all of those life values, paste them into the tool here. And don't worry, I won't make you sit through this. I'll fast forward it in just a second and pull up all of the other results for the second quartile, the third quartile, and the top quartile of utilization. This one's showing us, we've got a bit better of a predictor in terms of the shape parameter being over 2. It's now 3.17, and we have the age of 31,500 hours. So I'm going to repeat this for the other quartiles of utilization. Okay, so the eaters that we've got out of each quartile vary significantly. The accuracy of the data, or the predictability, has increased a little bit, but it's still not super useful. But one thing that did jump out when we were looking at the QQ plots, you'll notice that there's kind of three main clusters here, one up the top, one in the middle, one down the bottom, and they're each made up of 1, 2, 3, 4, 5 or 6 different kind of groupings or bands within those three clusters. And what that tells me is that there's something going on with the amount of the clusters that we've selected. So here, in terms of utilization, we've selected 6 different utilization values, and within that, there's 3 distinct groupings within that data set. And so what that makes me think is the other variable that we have 3 different elements to is the road type. So if I look at the road only of that subset, now we should just be looking at only one of these groupings here, and we should get much better predictability. So I'll paste the road values in and compute that. And so this is road high utilization, and we're getting a 16.99 on the shape parameter and 4,000. So I'll enter that into the charts for comparison. Okay, so I've run the numbers for the high utilization road, mud and dirt, and you can see that the 3 peaks are here with very, very high predictability. The medium utilization, road, mud and dirt, are shown down here. The predictability is a bit lower, but it's purely a function of how many utilization bands you select in the bucket that amalgamate to this result. So the point of this whole exercise is that even though you can see a random distribution, or what's close to random distribution, for a total population, the more granular you can go, and the better that you understand it according to a causal map or a causal model, and drill into those kind of branches by filtering on the data and analyzing the subsets, the better accuracy you can get from your predictions. But again, you can only go as far as what the data allows you to go. So there is obviously a limit to how deep you can go on this. The lesson here is that the failures aren't random. They appear random because of the limits or the boundaries placed on our causal model. Well, that's it for this video. I hope you liked the content. If you did, hit the like button. Subscribe to the channel if you want to see more videos. Thanks very much to the LinkedIn person for the question. And if you've got any ideas for future videos, leave them in the comments below, and I'll do my very best to make a video around whatever questions you have. Appreciate you. Have a good rest of your day.